the nonlinear activation function should not be a polynomial. Can you see why? Of? Yeah, so for example, suppose you have the activation function, which is the square. Then I can, if I have inputs into this activation function, sum of inputs, x1, x2, x3, x4, I can get only polynomial of order 2. Not more. Okay. All right. So I will see how you get essentially polynomials of arbitrary degree from nonlinearities that are not polynomials. Okay. But just to tell you a little bit in advance what is going to happen is that if you ask the next question, which is, okay, I can approximate any continuous function arbitrarily well, but how many units do I need? And the answer for shallow networks, but also for deep networks, is the number of units you need is in the order of so O to epsilon minus D, where D is the dimensionality of your inputs. You have vectors X from RD, and the number of, this is an upper bound, is in this order. This is also called curse of dimensionality. And you can see why. Suppose epsilon, the error you are ready to accept, is 10%. That is the maximum deviation from the true function. So, and suppose you have 20 dimensions. Then this will be 10 to the 20, which is a large number. Right? And this is only 20 dimension. If you are dealing with, for instance, CIFAR images, your inputs are, I think, 28 pixels. So the dimensionality is 28. Okay. So this seems to be this curse of dimensionality for a generic continuous function, if I don't know anything more, is of that order. We'll see that if I know that the function is smooth, for instance, it has bounded derivatives up to order m, then this becomes epsilon minus D over m. So this is smoothness helps. But it's not clear how much smoothness we have in many problems we are worrying about for that neural networks are good at. Yeah. Epsilon is the error you are requiring, the maximum error. Sorry?
Maximum allowable error.
Yeah. You are approximating a function, right? So there will be some error in the approximation, and this is the soup over the interval, epsilon.
What does this tell us about like C-infinity functions?
Sorry?
What does this tell us about C-infinity functions? Like completely smooth function?
So you say for its analytic functions, right? In principle, you could get rid of the curse of dimensionality for analytic functions.
But I mean, you should have like some kind of 1 over epsilon at least.
Of
1 over epsilon, you should have some kind of 1 over epsilon rate at least for the number of neurons that we need, right?
yeah.
The error goes to 0. But like this result seems to show that we need constant number of neurons to illustrate any like analytic function.
Yeah, this is an upper bound, but
I mean, like this is telling that if epsilon goes to 0, we still need a constant number of neurons to express any analytic function. If I get it correctly.
yeah, the framework is really for Sobolev spaces in which you have finite M, smoothness M, but for analytic function, in principle, you could do much better.
I'm saying that this is kind of contradictory. I'm not saying it's weak result.
Why contradictory?
Because if you have an analytic function, this bound is telling you constant number of neurons is sufficient to express any analytic function.
Mm-hmm.
But if we put epsilon to 0, if we go get epsilon to 0, then we should have more neurons, more and more neurons. We need more and more neurons to express the function, right?
Not clear. You know, for instance, I don't know, this is cheating, but I could have my nonlinear activation function being an exponential or a sinusoidal function.
Oh, you can change the activation.
I mean, these are general theorems for any activation function that is smooth.
Oh, I see.
But you know, for practical reason, there is this curse of dimensionality and there is this blessing of smoothness. But in practice, we cannot really count too much on the smoothness. And I'll tell you other things that are more reasonable. Yep. Oh, okay. So the other thing that is interesting is that although both deep and shallow network have this curse of dimensionality, there are certain compositional functions that I'm going to describe that are possibly the kind of functions that are expressed by convolutional networks, deep convolutional networks. For these functions, there are deep but not shallow networks for which the rate of approximation is in the order of is linear in D. Instead of exponential in D. Okay? I'll show you, this works for certain deep networks whose architecture is similar to the function that you want to approximate. Does not work with shallow, as far as we know. Okay. So this would say that for certain classes of function, deep networks, but not shallow ones, avoid the curse of dimensionality. Allora, so this, by the way, has this potential implication, is that this is the conjecture, is kind of blue sky conjecture, so take it as possible, but not clearly, possibly quite wrong, which is that the main reason why deep networks are better than, say, kernel machines is that they are better in problems in which you can exploit this advantage, the fact that they don't have a curse of dimensionality. And those are the problems in which convolutional networks do well. So, you know, another way to say this is that problems in which there is convolutional networks are not doing better than densely connected networks are also problems where well-engineered kernel machines do as well. There is some evidence for it. It's far from being proved. Empirical evidence. Okay. So shallow networks, just as a reminder, I mentioned this already, but I think there are at least two versions of this. We have networks like this, in which are really this equation. Graphs are a way to write equations, and this is a graph that just describes these equations where you have the units, there are R of them, are the kernels. Each one of the unit is, so to speak, storing one of the examples. If you have a Gaussian kernel, each unit there is computing the distance between x and xi, and then apply a Gaussian function to it. And then those activities, the output of the units, are combined by weights and added up. Okay? So that's a kernel machine. As you say, one layer of weights and one layer of units. It comes, of course, from a regularization problem of this type. And another example is say, Rlu network, in which you have activation function like this. And in this case, you have two set of weights, two matrices, W1 and W2, and the graph represents this equation where each unit is combining the weighted inputs and applying this activation function, and then it's adding weighted version of the output of the units. And I'm not, in most of the folly today or next time, I will simply neglect, as I think Sasha did, the bias, the BI, because you can always replace in the first layer the bias with one input, one extra input, which is a constant one. And in terms of approximation theory, it's enough you do it in the first layer. We can discuss that later. So you don't need the bias in the other layers. Okay, so deep networks, you may have things like this, as we have seen. So this would be graphs representing the iteration of what you've seen with two layers, where you have these matrices W that indicate, I think it's slightly different from Sasha, but similar enough. You have the layer is the underscript, like L minus 2, 1, this would be 1 here. Let me write it. And the other one will be, so KP will be the weight from unit K to input P. Okay. All right, so let's go through describing more carefully what I meant. In approximation theory, you have to define your target, which will be the function you approximate. And here I indicate up there a generic function f of x with a real valued output. It's just one output function in RD. And then on the right, you have networks that you can use, which are also function of a particular type that I can use to try to approximate my target function. I assume that the target function, as I said, is continuous. And for instance, in that case of one layer Rlu network, the function implemented by the layer will be a G, which is in the span, so it's a linear combination of these activation functions. All right, so as I said, the density problem is the one I consider any function into, say, the set of continuous function in 0, 1 to the d, and then saying that that set of one-layer networks is dense in it means that there is a G in the set of those networks such that the sup of f of x minus g of x is less than epsilon. And when I speak of degree of approximation, I'm asking again for this I'm looking at the and I'm asking how large is this, where this is the number of units on this network. So I can let's write theorem that is something relatively old. Is the curse of dimensionality one. If you have a function in this space, this is would be Sobolev space. So this would be the norm of f would be the sum I less than k less than m, and this would be the sum over I of derivative, including mixed derivative of degree k of f. So I want these derivatives to be bounded, functions with bounded derivatives. But I don't assume any structure on f. So the only thing I know is that f will be in a certain d inputs, one output. That's it. It's continuous. And then the theorem says that for any f in this space, there exists G in Vn. So G has the form G of x equals some weight sigma W. Let me see. This would be dot product. So this would be vectors. And there exists a G such that G of x minus f of x less than epsilon with n the number of units. So this would be here how many RLU units I have, and in the order of okay, so that's again the curse of dimensionality, as we have seen. Yeah. Sorry?
What was that notion of norm that you defined?
Norm? So this is a derivative, so all the derivatives
The norm is like this norm?
of the derivatives, yeah. Say I can define many numbers, it can be L2 norm. So this would be like
In the hypercube.
hmm?
On any point in the units.
Yeah, it's yes. Or on a ball. So this dk would be like df, d say k, df, dx1, dx2, dxk, all possible combinations up to order k. Let me give you just a couple of other examples of curse of dimensionality. If you have, for instance, a polynomial, so the space of polynomials, say, in d dimensions, so vectors with d entries, degree k, how many monomials you have in such a polynomial. You have d plus k monomials, which is d plus k factorial divided d factorial k factorial. And this is roughly, k to the d, these are very rough approximation, or d to the k. So again, if you have, 10, dimensionality 10, degree 10, you have in the order of 10 to the 10. Another way to think about curse of dimensionality, suppose you have a function of 10 variables, and suppose you represent it, which is the simplest representation of a function, as a table of values. You have to decide, how fine your discretization will be for each dimension. Suppose each dimension will be 10 partitions over a finite interval, from 0 to 1, 0.1, 0.2, 0.3. Then you have, again, 10 to the 10 numbers that you have to store in the table. So these are all the same, right? These numbers, this curse of dimensionality comes when you have a representation of different type, with polynomials, with discretization, and so on. Okay, let me give you a summary of the proof of how you prove this curse of dimensionality here. The first step, I'll give you first the logic of it. The first step is to show that if I have a shallow network, this is for shallow network so far, I have a shallow network with k units, and so I have Ci sigma, and this is in one dimension, so one variable. This is essentially a polynomial in the unidimensional polynomial of degree k minus 1. This basically says that with k units in a shallow network, I can represent exactly or within any polynomial of degree k minus 1. I think that's a key part of the proof. The other one, the next step, once you've done that, is to show that if you do the following, you combine, this is about polynomial, you combine I unidimensional polynomial where the variable in the polynomial is the dot product of w and x, this gives you a polynomial the whole space of polynomials of degree k in d variables. And the final step is to use some standard results that tells you that that with polynomials of this type, I can approximate with a certain rate Sobolev functions, so the space of function that we have defined with this norm with the derivatives. I think I want to do the first step. And the first step the theorem says that if sigma, my activation, is not a polynomial, and sigma is smooth, it's continuous, then the closure of VR, this is the span of R sigmoid in a shallow network. So it's this is the function produced by a shallow network with R smooth units. This contains this, I essentially said it already, is the linear space of unidimensional polynomials of degree r minus 1. And the proof is very simple. Is I consider the linear combination of two units. So one unit is ax plus b, and what I do, I take sigmoid of a plus h times x plus b minus another unit with ax plus b, and I multiply by 1 over h, and then I make h very small, and then and this gives me something like the derivative with respect to a of sigma a plus x b, which for a larger than 0 is x sigma ax plus sigma first derivative evaluated in ax plus b. So I have from two units I get essentially a monomial. This is a number. So I get a monomial x. From 3 units, the same trick will give me an x square, and so on. Sorry? is that if I combine in practice, this is not what probably happens in actual neural network. This is just a device for proving.
Yeah, yeah. But this coefficient, I mean, is itself variable. It's not,
Well, I just say h is very small, right?
okay, but I mean, it depends on x. It's sigma prime of ax plus b, the coefficient of this.
But this is a number.
But it depends on x, right? You want to vary x and say, argue that this thing is like polynomial in x, right?
What I want is to get x, right?
It's to something constant.
Yeah, the constant I can take it out later with the appropriate bias.
Yeah, but I'm saying this is not constant, right? The coefficient is not constant. It varies with x.
No, this is a sigmoid, a derivative s that evaluated at x.
Yeah.
So this is a number.
But x, aren't we changing x? What is the variable here? The function
Yeah.
we consider it as a function of x, right? And when we change x, we want it to behave like a polynomial in x, right?
Yeah, I can evaluate, for instance, let's see, in let me check. Yeah, I can, for instance, evaluate in a equals 0. And then I have just, then the only condition on the sigma is that the first derivative at b is not 0. There is another way to think about it, is which is equivalent, which is this is actually what you do in the second step. The one I mentioned, this one. How do you go? Here, you want to go from so the logic is that with unit in a shallow network, you can synthesize polynomials, the first step, univariate. Second step tells you that if you have univariate polynomials, by doing this trick, so the variable is univariate now, but is a dot product of w and x, I can synthesize any multivariate polynomial. This should be I. So a different coefficient. So that one, without going through it, but the bottom line is, suppose I have a simple univariate polynomials. Say, I can do the square. I have x plus y. I want to get x square. So if I have univariate, I can do x square. I can get y square. How do I get x times y? The way to get it is to do the square of x plus y, and then to subtract the square of x minus y. This will give me something proportional to xy, right? Do you see this? And basically, it's the same idea that having univariate polynomials in combination of more variables, like the coefficient be w dot a vector of x, y, and so on. So linear combination of the various variables, and then polynomials of this, I can get any polynomial I want. So so here is, we can go through it, but I'll go quickly because this is using formula that are available, well known, so I can synthesize, as I said, a homogeneous polynomial, so all terms of the same degree in d dimension by doing this combination of univariate polynomials. Just notice that this the terms in that combination, this pi, are a lot. R is the dimension of the space of homogeneous polynomials of degree k dimension d, which is, as we said, pretty large. So this means that, going back to our networks, polynomial in d dimension, degree k, can be represented exactly by a network with that order of units, lots of units. This is, by the way, exact representation. Polynomial is an analytic function, is an example. Okay. So now, for deep networks, the same is true in general. However, let's consider a class of function that, as an example, has this form. Suppose this is the graph of the function. This I have 4 variables. This is not a network, it's the graph of the function. So you have to think of this as, this whole thing, let me call it f, but this one, let's call it is a function f1, f2, f3. The output is real number, And so this is a compositional function in the sense that this graph corresponds to say this. I have f3 of f1 of x1, x2, f2 of x3, x4. Okay? It's a composition of functions. And I'll speak about constituent functions as f1, f2, f3. They are constituting the whole f. So the whole f is a function of 4 variables made up of composing functions of 2 variables. Does it make sense? Okay. You know, in a sense, there is an interesting question that will come out later, which is a bit open, is are all functions compositional or only some? What does it mean exactly? By the way, it's not clear, it's pretty clear that there are, when I write a function as compositional, there may be maybe not a unique way to write it. I can decompose a function potentially in many ways. But if there are, for instance, if I write, suppose I write an equation, a function of 2 variables, and I write it like something like a x1 times x2 plus b x2 plus c x3. And then I have, I don't know, this would be 200, the power. Okay, a shallow network will need a lot of units because there will be polynomial of order 100.
Our bound for shallow networks.
Sorry?
The bound that we had for shallow networks in this case would be like 2 power to 100 or 100 power to each.
Well, apart from the x1, x2, this will you will need at least 100 or so units, 101 or 2, right?
So you need 100, not 2 power.
Well, you need, let's see, it's k to the d, so this would be 100 to, it's 10,000 because you have the 2 variables. If it were 1 variable, it would be 99, but we have 2 variables. Yeah.
Yes, so the result we just proved, it was like an upper bound.
Yeah.
So any polynomial, we can get a neural network that has at least that approximates it. Do we have any lower bound result?
There are some lower bounds. Lower bounds are complicated because you have to show that, yeah. There are lower bounds. The proofs are complicated. I don't know them very well, but I can give you the reference. The bounds I know of are pretty tight, so there will be very close to the upper bound. So you cannot do much better in general. So in other words, there will be always some function that is pretty bad. Yeah. But there is an interesting question about the next results that I'll show about deep networks, because we don't have lower bounds. So it's an open question. If one of you finds a solution, let me know. So so the theorem that I want to for deep nets is again the same framework. So the functions are in W. Let me give this specific 2M. So now I have again this Sobolev space function with continuous derivative up to M, bounded derivatives. Dimensionality is D of the overall input, but it's a hierarchical networks in which the constituent function have dimension 2. That's the 2 there. So it will be a binary tree in terms of the graph of the function. Okay, so it will be something like this is the graph of the function, for instance, for 8 variables. D is 8. 1, 2, 3, 4, 5, 6, 7, 8. The 2 is because each of the constituent function has 2 inputs, and smoothness, assuming is M. So in this case, then the number of units I need for an approximation epsilon total will be in the order of d minus 1, and then is 1 over epsilon to m.
The assumption is that
Sorry?
the assumption is that the two variable functions that the field are big function from by combining them. That small function is in the Sobolev space of Wm, or the big function.
Yes, I really need just a Lipschitz conditions on those functions.
Results in like this. The results that the big function is in this Sobolev space.
Yeah. Yeah.
But we can't say like for all functions in the Sobolev space. Can't we?
The overall function must be in the Sobolev space.
And it should be representable in this.
Yeah. Yeah.
I mean, like there should be some functions that are not representable.
And the proof is pretty simple. Is basically says, I know that this kind of complexity I can approximate each of the continuous function of the constituent functions. Sorry, I can approximate each of them within epsilon by a shallow network that has this kind of so many units. Okay, that I know from the previous classical theorem. So when I add all of these units together, I get this. That's the basic story. What I have to worry about, and this is the only part in the proof I have to worry about, is that when I do an approximation of each of these constituent functions, there will be an error, right? I approximate each one of these, and I will have an error. And I have to check that this error do not explode. So the gist of the proof is this work with a mathematician who is in approximation theory since years, Rishikesh Maskar, and he calls it this good approximation of errors. Essentially this showing that errors don't explode. And if we consider, it's a pretty simple proof. If we have, say, let's call H1 this function, H2 this function, these are constituent function, H is the overall. And I assume that H of x minus H of x plus epsilon is less than some Lipschitz constant time epsilon. If the function is as continuous derivative, that's follow from that. So then I know that H2 and the same for H1 can be approximated by my network, let's call it P2, with precision epsilon, and I want to check how much is H of H1, H2 minus P, P1, P2. So in other words, P1 and P2 are approximation of H1 and H2. P is an approximation of H. P2 and P1 will have some error. I want to see what happens to the total error. And so I write this as I'm rewriting without changing anything. But I add and subtract this. And then I see that this one to be, because of this property, will be less than L epsilon, and this one is, I know that H, one of these constituent function for the same inputs will approximate P within epsilon, so this will be also plus epsilon. And so this is in the order of epsilon. Sorry?
You have like k layers.
Yeah, this is doing this just for two, but you
I
can.
mean, like, does it become, does the bound that you prove is like expansion?
Yeah.
Okay.
Yeah, you can check it out.
The Sobolev condition.
Sorry?
The Sobolev being in the Sobolev space implies that all of these small functions are Lipschitz or
Yeah, if you have a continuous derivative, they're Lipschitz, yes.
But L can be potentially large.
Bounded derivative. Hmm?
But L can be potentially large.
Yeah, in principle, yes. Now, if you look at RLUs, L is 1. But yeah, this proves, by the way, work for RLUs or other nonlinear function. And they work for RLU, important thing that maybe I have not stressed, assuming that they are smooth, which is not true RLUs. You know, like you're smoothing the corner. This is just, it's a technical assumption that we need. For instance, remember when we take essentially a linear combination, which is a derivative of the sigma, we need smoothness there. And in fact, one of the things I will address is how to generalize, extend this to non-smooth RLU. It is a technical, almost certainly just technical, because you can see that you can, you just need to comply with the assumption to smooth the corner in the RLU very, very locally, as local as you want. This will not change what happens when you do simulation in the computer. And for instance, we have actually done some empirical work in which we have approximated the RLU with a polynomial, so very smooth, replace it and got exactly the same behavior on data set like CIFAR or so. So it's very likely that's nothing major, this assumption, but let me try to finish there is one thing, let me see if I have it. Yeah. This goes to the heart of if you think back at these binary trees, a number of remarks. One is at binary, so I had the constituent functions having dimension 2. That theorems, everything work for other dimensions, like 3 or 4 or 5. The important part is the dimensions of the constituent functions must be fixed and small. Okay? You can build out of constituent function with fixed dimensionality. You can build hierarchically functions with arbitrarily large dimensions. That's what we can do with the binary trees. But what controls the approximation, how many units you need to approximate it, is the dimension of the constituent functions. So that's remark 1. Remark 2 is that convolutional networks, like the one you use in CIFAR or ImageNet, have that structure. There, instead of 2, you probably have 3 by 3, so 9. That's the kernel typically used for these images. But the same considerations apply. In convolutional networks, unlike here, you typically have weight sharing. So weight sharing means that when you have graphs of this type, the function h1 and h2 are the same. At each level, you have all the same function. That's weight sharing in this framework. So the interesting thing is that in order to get this result, which means you don't have curse of dimensionality for deep networks which have the same architecture as these compositional functions. You don't need weight sharing. Weight sharing will help even more because, of course, you have fewer parameters. But what makes the exponential dependence on dimensionality go away is not weight sharing, is the locality of the constituent functions. The fact that I have a fixed dimensionality, number of inputs. That's was a bit surprising to a few people, like Joshua Benja, for instance, the fact that does not depend on weight sharing. Now, this particular structure of compositional function I described, like this one, repeated, so binary tree-like, is only one of the possible ones. It makes a lot of sense for problems that can be decomposed in parts. It's like if you read the text, you have letters and words and sentences and so on. You're composing more complex things out of simpler constituents. In vision, you can imagine you have, parts of objects, scenes, and you don't need to analyze this pixel together with this pixel. You can analyze small part of the image, compute something, and then combine this computation. That's what networks of this hierarchical type do. So it makes sense that the underlying function in these problems is the ones that neural networks exploit is compositional in that particular sense, and even invariant, so weight sharing, invariant to translation. But you cannot expect all functions to have this structure. So in fact, convolutional networks are used in things like text, speech, images, so it's quite intuitive. You have this kind of hierarchical structure. But if you have to analyze, for instance, financial data, I don't expect that convolutional structure or hierarchical structure to be there at all. On the other hand, the results I've discussed can be used for any direct acyclical graph. So if you have a function that is described by a graph, so you have a function here of free variables, and then gets the input to other functions, complicated way. As long as the graph is a direct acyclical graph, everything I said holds. Depending on the graph, you may or may not have an avoidance of the curse of dimensionality. So,
For DAGs, you can't.
sorry?
For DAGs, you can't have the curse of dimensionality. For this type of graphs, can we have the curse of, still have the curse of dimensionality?
Yeah, it could be. It depends on the dimensionality of the inputs, for instance, right? How large that's a problem, and how much you can exploit the fact that this overall function has a structure. In general, what happens here, let's go back for a second. What happens is, I know something about the function that is, for instance, a binary tree, say, my first example, right? And the function graph is a binary tree. This is prior information. This information, it's something that a shallow network cannot exploit. Somebody of us comes with a way to exploit it, let me know. But I don't see how I can exploit this in a shallow network. But a deep network can exploit it by essentially copying that architecture. And if you do this, in that particular case, you get to avoid the curse of dimensionality. My guess is that if you have some other graph structure that you know or you guess a priori about the function and you implement it in the architecture, you'll also gain. I don't know whether exponential or not, but you will gain. So that's a general rule, and I think it would be interesting to think about, I don't know of any examples apart the convolutional networks where the architecture, is designed on some prior that turns out to be good for a large set of problems. It's probably quite unique, but I expect there will be problems for which you have some prior information about the structure of the underlying global function, and where by knowing that you can design neural network architecture that exploit it. So keep this in mind. I don't know such examples, but it would be nice to come up with one. Want to mention one last thing before letting you go, and this is another to-do. For anybody who's interested, is a conjecture. So there is just very recently, people have mathematicians have become interested in trying to see how good RLU are, the discontinuous RLU are in approximating functions, even univariate functions. So some recent paper, not yet really published, but on arXiv, by Dobeshi, the wavelet lady, and a couple of other very good mathematicians, and they show that there can be a very unconventional way, but effective way to approximate function. Unconventional because typically people have used smooth function for doing approximations, like wavelets or splines or so. And so there begin to be some result in the literature, and there are this theorem that says that you can build an RLU networks that can approximate any function in the usual Sobolev space within epsilon, and with a depth that has this structure. So this is the usual curse of dimensionality, and then it has this depth. But now, the idea is that you could replace the first two parts of this theorem I was showing, that was based going from shallow networks through polynomials. Instead of that, use directly this to go to the approximation. And when you use this in the deep networks, you should be able to prove this conjecture that that you can use discontinuous RLU with the same results that showed before, but instead of at each node, instead of having a shallow network, you may have to have a RLU network with a small depth. So in other words, you can get rid of the assumption of a smooth RLU by using this result. Sorry?
This log factor only adds up to...
You pay this log 1 over epsilon depth, but yeah. And what needs to be done in order to prove this is to make sure, and should be pretty easy, that you have a good propagation of error in this type of network, which is not anymore a shallow network, but a non-shallow one. To me, it seems pretty easy, but the devil is also always in the details. Okay, let me just check, but I think yeah, let's finish here. There are some interesting questions about computer science and compositional functions, like recursive functions, and about there are similar results to this for Boolean functions. These are all kind of research projects that not so important for the class. Yeah.